Here is the solution to the bobsleigh question then. So our first question, first part of the question says, explain why a resultant force is required when this object of mass m moving with speed v around a circular path of radius r. It has that magnitude of resultant force. Why must there be one? Well, as we said before, the direction is changing, so the velocity is changing, so it must be accelerating. And so by Newton's second law there must be a centripetal force. And the centripetal is not absolutely necessary here, because it doesn't ask for the direction. Oh yes, it does. My apologies. So there you go. Velocity is changing, 1 mark, so it's accelerating, so there's a resultant force towards the center of the circle. So the resultant force bit, you're told there is one, so you don't have to say that to get any credit, or rather there is no credit for that, but it is towards the center of the circle. Let's make that bold so we see it's the answer. So the next part then, when vehicles corner on a level road, the resultant force is provided by friction. For a given vehicle and road surface, that should say road, the friction cannot exceed a certain maximum value. Use these facts together with the expression for the resultant force to explain why roads designed for high-speed travel have no sharp bends. Well, a sharper bend, no comma there, means smaller radius of circle, of course. F has a maximum value that it can be. So as R falls, oops, V must also fall, so that the centripetal force required does not exceed the maximum. Since F equals mv squared over r. So there you have it. Let's tidy up a little bit here. Maybe get more of the question on the page. So then we have the bobsleigh. And here we have the center of the circle around which the bobsleigh is going. And the bobsleigh is at some angle to the vertical or the horizontal, as you choose. We have the angle to the vertical measured here. So here's a free body force diagram. We have a normal reaction at an angle to the vertical here. We have the weight acting down because it always does. And we're asked to write down an equation expressing the condition for no vertical acceleration. When you look at this diagram, you say there are two forces acting. There is the normal reaction, there is the weight. And if there's going to be no vertical acceleration, then the weight must be exactly opposed by the vertical component of the normal reaction. So in this case then, n cos theta, the vertical component of the normal reaction, must equal the weight. And there we have it. Write down an expression applying Newton's second law horizontally. Well, you have n sine theta is the horizontal component, and F equals n sine theta. There is no other force opposing that, so that is our centripetal force. So we could write down that n sine theta equals mv squared over r equals F. F equals n sine theta might do it, but certainly putting in the mv squared over r can do no harm. So hence show that tan theta equals v squared over rg, and it tells you that tan theta is sine theta over cos theta. Hence means on the basis of what you have done to this point, go further and show this expression. You're told that tan theta is sine theta over cos theta. So I'm going to divide this expression by that expression. So I'm going to do my n sine theta over cos theta. And I'm going to say that that equals mv squared over r and that is divided by mg. Now if I rationalize that expression, I'm going to get mv squared over mgr. And of course, the m's will cancel, which will give us v squared over gr, or v squared over rg. It's the same thing. So we have proven the expression. And then finally it says, calculate the value of theta. Well, that's simply a matter of substituting the numbers in. So you have V is 30 meters per second, so 30 squared divided by 20 times 9.8, and it's the inverse tan of that, which gives you 77.7 degrees. We've got 3 sig figs for the V and the R. We could give it to 2, we could give it to 3. We do know G to 3, 77.7, I think 78 degrees to 2 sig figs, because we only have G, we're only given G to 2 sig figs. 78 degrees. There it is.